Good morning, everybody, or for some of you, evening or afternoon. My name is Peterson. I will be giving this month's global online seminar in Biodiversity Informatics. This series has been ongoing for 4 months now, 5 months, and I believe it's seeing quite a bit of use and appreciation. So we'll be continuing it. Next month's seminar will be on the 28th of August. It's the last Thursday in August, 9 a.m. Kansas time, which seems to be kind of an optimal time around the world. And I'll be announcing the speaker for that seminar quite soon. I'm talking to you this month from the Universidad Austral in Valdivia, Chile. So I'd like to thank my hosts here, particularly Sergio and Maximiliano, for making me and my family so comfortable. And it actually feels a little bit strange to be giving a seminar in English. So this is my home away from home for the next few days. Last point before I begin the seminar is that if you have questions regarding the seminar, you can email them to me at the either biodivtraining@gmail account or my own account, which is town@ku.edu. So we've done a series of seminars that have been about research topics, either research in biodiversity or research on the informatics side. This month I wanted to focus a little bit more on the methodology side. With colleagues over the years, several different laboratories around the world have been working quite a bit on essentially improving the methodologies for estimating ecological niches and predicting geographic distributions of species. I'm going to go ahead and start the presentation just so that I can have the benefit of a few visuals here. Okay, so this is essentially an update of methods, and the reason I do this is that it's pretty easy just to find some occurrence data, find some geospatial data, maybe climate data, download a very easy to use modeling tool and push the button and interpret the results of pushing that button pretty simply and without a lot of thought about what went into the process. And essentially what I'm going to do is argue against that. I'm going to give you a bunch of ways in which the methodology needs to go beyond just pushing the button. Basically, in order to develop robust models of ecological niches, what we need to do is frame the process of developing those models in the context of ecology and biogeography. So let's jump into this. But I'd like to give some credit to begin with, and that is to this group, plus or minus a few individual personalities, which is to say some of the group are not represented in this picture, but this is the University of Kansas Ecological Niche Modeling Group. They don't always dress in saris and suits, but this is the group that has done a lot of the work that I'll be presenting to you this hour. So let's start, sorry about the Spanish language slide, it means basic concepts. Let's start with the basics, which is to say I need to give you a framework of terminology to be able to explore these ideas. So let's jump into it. The first concept is that of spaces. In ecological niche modeling, we have two linked spaces that are very crucial. One is a geographic space, and the other is an environmental space. So we usually think about distributions of species in terms of maps, and that's very much a geographical phenomenon. So here's a map of the world with shading representing temperatures, and it also has a lot of random points strewn across it. Well, that's our linkage. Those points are a linkage to an environmental space. So there's the map. Here is the distribution of those sites across the world, those random points. But now we're looking at the distribution in an environmental space. This is a very simple one. Precipitation on the vertical axis and temperature on the horizontal axis. And essentially what I want you to notice is two things. One is that this is most definitely not a normally distributed distribution, which is to say it's very skewed in both directions. Second is that there are areas of dense concentration and areas of sparse concentration of points. And that's going to complicate our lives enormously. But again, think about all of this work as being done in two linked spaces. We look at distributions of species on maps. We fit a model in environmental space. And then we go back and visualize our results in maps again. So this is really a complex process where we're going to be jumping back and forth between these two spaces. Now, we need a little bit of terminology here. We can think about the requirements of a species with respect to abiotic conditions, temperature, humidity, rainfall, time, things like that, things that are not linked to the population of the species in question. We can call that that set of requirements A, and this diagram would be a map in geographic space of the areas that are suitable for our species with respect to A, with respect to abiotic requirements. Now, our species may also have requirements in biotic terms. And so we introduce this second circle, B, which is the set of areas that are suitable for our species when you consider interactions with other species. But notice that those interactions will depend in their strength and influence. They'll depend on the numbers of individuals of our species. So that's a much more difficult area to reconstruct. Where A and B overlap, which is this eye-shaped area in the middle, that we can consider the potential distribution. It's where the abiotic and biotic situations are both correct simultaneously. But there's a third consideration, which is movement. And so this green circle at the bottom represents the set of areas that are accessible to our species. It might be a continent, it might be an island, or it might be part of a continent or an island. But what you can notice is that M, these accessible areas, cuts the potential distribution into two areas. One part is accessible, and so that's going to be occupied. And the other part is not accessible, and that's what we'll call the invadable distribution. So we have a whole set of terms for different distributional areas. So now we can go on and think about niche modeling in that set of distributional areas. So we call that diagram the BAM diagram. And at the lower left, you can see how we usually draw the BAM diagram, which is three overlapping circles that are quite symmetric. But I already mentioned to you that biotic interactions are extremely difficult to replicate, and particularly on geographic scales. And so we've made the argument that those biotic interactions on geographic scales, at continents or major areas, those biotic interactions are not a major constraint on the distribution of species. And this is what we call the Eltonian noise hypothesis. Essentially, that the constraints are going to be either the abiotic niche, which you can see in red, or accessibility or mobility, which you can see in pink. And so within this diagram at the upper right of this slide, what you can see is 3 different configurations that these 2 circles could have within a broad, non-constraining circle, which is biotic interactions. So this is essentially the world in which we work normally in these correlative ecological niche models. It's essentially a world in which we assume that biotic interactions are not frequently limiting as far as geographic distributions of species. So now I'm going to throw one equation at you, but it's an important one. What we're really interested in is this term in the middle, the fundamental ecological niche, or N sub F. But what we have to remember is that we observe that fundamental niche against a background of the accessible places and their environments. And so that's this last term, eta of M. So eta of means environments associated with. And so what we're saying in this equation is that we can only observe part of the fundamental niche, and that is the part that is manifested across M. And so what we can observe is this first term, N star sub F, or the existing fundamental niche. And so that's the part of the fundamental niche that's actually visible and observable across the distribution of the species. So I just want you to remember that we may not always be estimating what we really want to see, which is the fundamental niche. And just to give you a bit of an example of that, in this slide, I'm showing you all the climates of the world, the same diagram that I showed you a little bit before. I'm in southern Chile, so I decided I'd show you a species of bird that's endemic to Chile, or almost endemic, and that is the genus Pteroptochus. It's a family that's almost endemic to Chile. Up here at the upper right is a hypothesis of its accessible area, or M. And when I look at that area down here on the world climate diagram, the red squares indicate known presences. Well, the green triangles show you the environments that are present across that species accessible area. And that's the point of this. I can see the part of the niche of Pteroptochus castaneus that is manifested across M. I can see a little bit of M down here in the lower left corner that is not occupied by the species. But really, I don't know if the niche of this species extends further to the right, which is to say to warmer temperatures, or further up, which is to say to wetter areas. And so that's the whole idea about the fundamental niche being only partially observable. And so if I were fitting ellipsoids to this species, I really don't know whether my ellipse might look like this blue ellipse, which fits pretty tightly to the points, or this green ellipse, which is a little bit bigger to the right and upward, or this red one, which is huge going to the right and upward. I simply don't have any information about that. And so that's an introduction to basic concepts, which should serve us pretty well. One last comment is that if ever we want to compare niches, maybe of species 1 and species 2, you would think that we would just need to say, well, is the fundamental niche of species 1 the same as the fundamental niche of species 2? But what you have to remember is that we can only observe the existing fundamental niche. And so really what we have to ask is whether the fundamental niche of species 1, given the environments available across its M, is the same as the fundamental niche of species 2, given the environments across its M. So that's the contrast and the quandary we're put into. Basically, that it can be very hard to estimate the ecological niche, and we may frequently be observing and estimating something that is related to the ecological niche, but it's a subset of it because of incomplete representation across M. So there's our introduction to basic concepts in about 13 minutes. Now, what we want to do is go through the process in 5 major steps. So the process of ecological niche modeling can be distilled down to these 5 steps. Essentially, accumulating input data, integrating the occurrence data with the environmental data, calibrating the model, evaluating the model, and summarizing and interpreting the model. Okay, so we're going to go through each of those steps in the rest of this talk. So, in that first step, we talked about accumulating input data. And essentially here I've drawn out the steps. Regarding occurrence data is at the top. We collate primary biodiversity data. Those are data that place a species in a particular location at a particular time. So we get together those data from wherever. We should assess the spatial precision of those data and the quality of those data. Essentially, are they ready to be used? And we're going to throw out a lot of data. And then we're going to want to subset those data, preparing for model evaluations. We'll deal with those later. On the side of the environmental data, which is the bottom swath of this slide, we're going to, again, collate relevant data. These will be raster GIS layers that summarize aspects of the environment. We need to measure and evaluate spatial autocorrelation in those layers, and we may be able to process the raw environmental information so that the layers are maximally relevant to the distributional ecology of the species in question. And notice that we're going to see a little bit of linkage between these 2 processes in that our assessment of spatial autocorrelation is going to affect how we subset data for evaluation. Okay? So that's the first of 5 overview slides. I'll give you a little bit of detail about it. Let's talk about occurrence data. Our goal is to represent the full diversity of situations under which a particular species can maintain populations. We shouldn't be too upset about spatial biases, but we should be very, very, very careful of biases with respect to environments, because biases with respect to environments in the sampling or in the availability of data will translate directly into biases in estimates of niches. So more occurrence data is usually better, but not always. Sometimes it's better to have much less occurrence data, but much more in terms of balance and even sampling across the environmental landscape. I just want to point out that we frequently lose a ton of data, a big portion of our data, along the way. This is just an illustration. This is the species link network, which is a very large scale and very well designed data source for Brazilian biodiversity data. You can see it's been in operation for 12 years now, from 2002 to 2014. The green curve shows you the total number of data records online for Brazilian biodiversity. And you see they're almost at 7 million records. But the blue area is that portion that is georeferenced. And notice that that is more down at 2.8 million records. So notice that we're losing more than half of the data simply because there's no georeference attached to the data. When we do georeferences, we have to take into account uncertainty. If I take a locality like 5 kilometers north of Valdivia, Chile, I have to consider what north means. North probably means more north than northeast and more north than northwest, but it doesn't mean exactly north necessarily. And when I say 5 kilometers north of Valdivia, I don't mean exactly 5 million millimeters. I mean probably more than 4 and less than 6 kilometers. Okay, so we have to take into account a lot of sources of uncertainty. Also, Valdivia is not a point. Valdivia has a significant footprint. So we really have to be very honest with ourselves and with others about the fact that georeferencing has to represent where the species was found, but also has to represent the uncertainty with which that place is characterized. Other things that it should do is summarize the methods used and preserve all of the information, because we may need to reinterpret the information at some point. That's a bit of generality about georeferencing. Now, even when we get georeference data, I told you we want to be able to look at the precision of those data, and so you need to make sure that the data source where you get your data provides information about uncertainty, and not all of them do. But let's say we get a bunch of georeferenced occurrence data. These are data for that same genus Pteroptochus that we already talked about. And you can see it's a genus that's almost endemic to Chile, has a couple occurrences that leak over into Argentina. But really, we see a lot of information. But then we see some outliers. So look at these points that are flagged by the red arrows. There are 2 views. You can see an outlier that's much farther east into Argentina in the north, and another record that's way, way south in Patagonia. At a finer level, this upper right red arrow points us towards a green triangle that's off the coast of Chile. And these are not marine birds, so we can guess that that has some sort of error in it. But also notice that the nearest green triangle is far away to the south. And by the same token, in the left-hand side of this slide, you can see a purple circle far south in the range of the green triangles. And so those records may be with incorrect georeferences. Maybe it's the wrong latitude and longitude, or they may be the wrong species identification. And in all of these cases, what we're doing is we're looking for outliers. We're looking for things that might hold error. Another trick that we can do, this is with some data from Kenya. Most of our biodiversity data come with textual descriptions of the sites, so like the country and the state and the county and the place. And so we can do things like plot out points based on their georeferences, but color those points based on their textual description of state or district. So here in a map of Kenya, look at this northeasternmost district. And you can see that those blue circles are the only thing that we see there. And so that is a province that was essentially correctly georeferenced, and the data were correctly georeferenced, such that only things with the name of that province show up in that province. Now look at this northwesternmost province. We see mostly these green circles, but we also see these light green circles and some purple circles. Uh-oh. And in fact, we also see these green circles farther south in the next province. So what is this telling us? Well, we don't know. We know that something's wrong. Either the name of the province is wrong, district, or that the georeference is wrong. But what I would suggest to you is that those records have a higher probability of containing error than do the records where the textual description and the coordinates concord. So this is essentially just a way of looking for inconsistencies that may point us towards error in our data. So essentially what we do with data after we've georeferenced is we attempt to detect records that have meaningful error, which is to say error that could mislead us. We can use internal consistency within the data set. Do the species names make sense, and are there no misspellings and things like that? And we can do these exercises to see whether the georeference matches the general habitat preference of the species. Is a terrestrial species on land and a marine species in the ocean? And also, do the coordinates, the geographic coordinates, match the textual description of the country or the state or the district or what have you? We can also use extrinsic data, essentially data that are external to the data set. We can ask, do the occurrence data match the known distribution of the species spatially? And we can ask, do the occurrence data match the known distribution of the species in terms of environment? Obviously, we're going to throw out the records that are very imprecise in terms of their georeference. And I just want to emphasize that data cleaning is an iterative process. It takes us time to go through over and over and over again these records and get rid of as much of the noise as we can. So you can do a little bit of reading about occurrence data and such in this paper. I'll make all of the papers available in the form of PDFs. But this paper basically provides you with a little bit of discussion and a very useful concept, which is a metric, capital E italicized, and E is a measure of how much error is likely to be present in a data set that you're using for analysis. I won't go into the details of E, but we're going to use it at several points downstream in this talk. Last point is we want to subset our data to permit a model evaluation exercise. Essentially, anything can produce a model, but the question is, does the model have predictive power? And so we definitely want to do some sort of step of data subsetting that responds to the question at hand. Essentially, we need to subset our data in such a way that it speaks to the use we want to put our model to. I'm not going to go into great detail on that for lack of time. Regarding environmental data, I'm going to move pretty quickly through this, but it has to be in raster format, which is to say it has to have data across the entire region of interest. And it should be relevant to the distributional ecology of the species. We don't want too many dimensions. We definitely want enough dimensions to describe major features of the ecological niche of the species. But correlated dimensions, collinear dimensions are bad, and too many dimensions are bad, simply in the sense that they confuse most of the modeling algorithms. We can get all sorts of sources of environmental data. It could be climate, they could come from satellite data, topographic data, soils data, etc. We need to be cognizant of the degree of spatial autocorrelation in our data. Here I'm showing remotely sensed data at 250 meters resolution on top of climate data at 17 kilometer resolution. And all I want you to appreciate is the incredible diversity in the pixels in the remotely sensed data, and the almost zero diversity in the climate data. So we need to measure and contemplate spatial autocorrelation because it can cause not only non-independence in model evaluation exercises, but also it can inflate our sample sizes artificially. You can read more about spatial autocorrelation and those issues in this paper by Boria et al. Last point about environmental data is that we should avoid the temptation of just using the same data layers over and over and over again. It's very common in this field to simply grab the bioclimatic variables from the WorldClim data set. And I would argue that's not a good idea. Not that they're bad data, but that we oftentimes know something about the ecology of our species, and we can design climate-based data products that speak more directly to the biology of the species. Agronomists have been doing this for years and years. These are just some examples that I grabbed off of the web. Growing degree days, average date of first freeze, earliest onset of cold temperatures in the autumn, just things like that that may allow us to develop a more relevant view of environmental landscapes that may speak more directly to the distributional ecology of our species. Okay, second major panel in this process is kind of putting together the environmental data and the occurrence data. And this is something that really hasn't seen much attention except for a couple recent papers by this study group that I showed you a picture of at the beginning of this talk. We'll start with this paper by Saup et al. And essentially what this paper does is it says that we need to think very carefully about the BAM diagram, the configuration of those three circles that a species is probably subject to. I'm not going to show you much of this paper simply because we don't have much time. But I already introduced you to the idea of the Eltonian noise hypothesis. And so that reconfigures our BAM diagram to be basically just the relationship between A and M, as I've shown on the right side of this slide. So there are four ways that two circles, A and M, can relate to one another, and we've given them kind of funny names. But those four circles, we may easily find species that are distributed under those particular circumstances. And so in this paper, what we tried to do was to see how successful modeling algorithms will be given these different configurations. So without going into a lot of detail, we created imaginary species, hypothetical species. I'll call them virtual species. And then we imposed, so those species were basically a niche and its footprint on the Earth. And then we imposed on those niches and their potential distributions, we imposed different M hypotheses. So this would be a classic BAM hypothesis. In blue and yellow, you can see the potential distribution of this imaginary species. And what we've said is that the yellow areas are accessible and the blue areas are not. So this would be essentially a classic BAM example. And what I want you to see, here are those four different configurations. I want you to see that these different configurations have very different implications for the success of modeling efforts. So in these diagrams, prediction of the potential distribution is shown on the horizontal axis, and prediction of the actual distribution is shown on the vertical axis. and a perfectly random prediction would be down here in the lower left corner of each graph. What I want you to see is that under classic BAM, the CB, and under HD, which was the Hutchinson's dream, our models are doing a pretty good job of getting out towards perfect prediction, which is 1.0 on either of the axes. But for the other two scenarios, what we called All OK and Wallace's dream, notice that most of the model results are down near 0, which is to say most of our model results are not better than random. That is very, very worrisome. So what we conclude is that there are some BAM configurations that simply are not amenable to fitting niche models. I'm not going to go into the bit about fitting potential versus actual distributions, but we really do need to think very carefully about what is the BAM configuration likely to be before we start into a study, because some analyses, some situations simply don't lend themselves to fitting niche models. So here's a second aspect of integrating the two types of data that we're working with. And this is, again, a product of that working group that I showed you at the beginning of this talk. And this is referring to the role of M, essentially the accessible area. I'm not going to go into the details of the test that we did, but suffice it to say that we created a species, another virtual species, with known niche, but we calibrated and evaluated and compared models within a series of areas, exactly coincident with the known niche, which is this 0% line, 5% larger, 10% larger, 20% larger, etc., etc. And all I want to show you very briefly is that everything we do in niche modeling depends on this assumption of your calibration area. So for example, this is comparing with the broadest area. This is how similar the maps are. 1.0 is perfectly similar, and 0 is essentially random with respect to one another. And all I'm showing you here is that comparing with the map based on calibration across the broadest area, none of these maps is particularly similar. So the calibration area makes big differences in the actual map that results, in the distribution that we predict for our species. If we are evaluating models, and I'm not going to go into the details here because we haven't talked about model evaluation yet, but what I want you to notice, if 1.0 is the really crucial value, where 1.0 is essentially a random value, at a 0% buffer, we have the distribution centered on random, but at 20, 40, 60% buffer, the larger buffers, we get a significant result. So, you know, the horrible thing is, if you want a significant model prediction in niche modeling, you simply evaluate over a broader area. That's not honest, and that's not science. If we're comparing models, and again, this is something I don't have time to go into, but if we're comparing models, we get the same thing. In this case, the critical value is here at about 0.42. Notice that 0% buffers are pretty much centered on that value, but by the time we get out to 40 and 60% buffers, our null distribution is lower than, and we would conclude significant similarity in these two models. Again, no time to go into it. I just want you all to be aware of the fact that all three of these major functions in niche modeling depend very crucially on the calibration area and the evaluation area. These are things that are usually not even mentioned. Why did you calibrate across all of Mexico or across all of Eurasia? and not across a rectangle or across a biotic region. At the very least, these are assumptions that need to be stated explicitly. So no time to go into how we estimate M. I recommend that paper, the Barve et al. Paper, 2011. Suffice it to say that we don't have a good way of doing this yet. We're working on it. But also suffice it to say that it's much better to have explicit assumptions than hidden implicit assumptions that are not stated. The sampling that underlies our data ends up functioning much in the same way as M. Suffice it to say that we need to take into account that sampling. This is a view of an oriole species, a New World oriole in Mexico. And all I want you to notice is these big concentrations of observations. And where are they? Well, they're in the US portion of this species range, California, Arizona, and southern Texas. And also, they are in tourist areas. Here's Cabo San Lucas, here's Puerto Vallarta, here's Riviera Maya, Cancun. And so essentially, this is a species where it's much easier to get presence data in areas where birdwatchers go. And we have to take that into account, or we're going to create the same biases that an improperly designed M hypothesis creates. And I had already mentioned to you the idea of reducing dimensionality. Oftentimes that's done using principal components analysis. Sometimes it's done using an assessment of correlations among variables and essentially throwing out single variables. But this is a very important step. Okay, third major panel in this talk is about model calibration. I just want to mention a couple of things here. I want to show you some work that is presently submitted for publication. The leader in this project was my colleague Huijie Chao in China. Also involved is Jorge Soberon. But essentially, this is perhaps an important point that maybe a bunch of people haven't appreciated. The optimization literature has a lot to say about what they call no silver bullets or no free lunches. And it's essentially just the idea that everything has a cost to it. And so very rarely will one tool be the best tool for every... I'm busy. Very rarely will one tool be the best tool for all of our challenges. And so what we've done, just to illustrate this, is to create a bunch of virtual species. Those are the climate combinations across Eurasia and the niches, and a bunch of virtual niches associated with them. We can have small niches like these or big niches like these. And this speaks to a result that was published in 2006 by Elif et al., where essentially they line up a bunch of algorithms, they give them a predictive challenge, and they measure average performance. So that's what we're seeing in this graph. And this paper has been cited literally thousands of times. Well, we can do the same with the results of this exercise, and we can see this is by different algorithms. And what we can see is that some of these algorithms are better at avoiding omission, which is on the vertical axis. Some of them are better at avoiding commission, which is on the horizontal axis. And we can see a lot of differences in average performance. Well, we can look at the same data in a different way. And this goes back to that idea of no free lunches. It's saying that probably no algorithm is going to be optimal for all of these species. And so instead of looking at average performance in this study, what we did was we looked at, for any given species of the bunch of species that we evaluated, how frequently does each algorithm come out as the best? And so this is using two different metrics, kappa and true skill statistic. This is measuring best in terms of the potential distribution A or the occupied distribution GO. And across the bottom you see the different algorithms. And essentially what you see is that each algorithm in some case for some species was the best. And no algorithm was the best in all cases. And so that leads us to what we can call no silver bullet thinking or no free lunch thinking. What it suggests is that we should not use just a single approach, even though that's what a lot of us do. Rather, what we should do is implement a series of approaches, a series of algorithms, challenge each one of them with a predictive challenge, and choose the best approach for that particular situation. Very frequently, people are using MaxN. It's in about 2/3 of the published studies these days. And MaxN is great. I really enjoy the user interface. The models appear quite powerful. But no silver bullet thinking suggests that MaxN will be best only some of the time, and that some other algorithm using some other type of processing will probably be best at other times. So essentially the idea, and this is a lot of extra work, but the idea is implement a bunch of algorithms and decide which is best. Use that algorithm. For model thresholding, we're going to keep this very simple. This is a probability tree, and it's meant to emphasize to you that the route that a biodiversity element takes to becoming a presence record involves a yes answer to each of these questions, essentially the green ball in each of these branches. And so what you can see is that only one of these outcomes leads to a presence record, but a lot of outcomes lead to absences. And so what that means is that absence data are cheap, and absences will frequently be generated by processes that don't have to do with abiotic suitability. But presence data have to pass all of these tests. So what we want for thresholding is an approach that prioritizes omission error over commission error. There's an approach called minimum training presence thresholding, which seeks the highest suitability value that includes all of the calibration data. And that's most of what we want. But what we have to remember is that our calibration data probably have some error. And you'll remember that we measured that error as E. And so what we really want to do is seek the highest suitability value that includes 100 minus E. So if we think that our data probably still have 1% error in there, that we just couldn't ferret out as we were doing our data cleaning, well, we should probably seek the highest suitability value that includes 99% of the calibration data. So that's a very simple approach that prioritizes omission error over commission error. And then a very last point is, even when we've chosen the right algorithm, we still have to choose parameters and optimize that algorithm. And so this paper gives us some first indications about how we might do that. Again, I'm not going to go into detail about this. Okay, fourth panel, model evaluation. And this is simply thinking very carefully about what is a model and what is a good model. And a good model, I would submit to you, is one that can predict independent information. So if I'm an archer and I'm shooting at these two targets, who's better? I would be much happier with myself if I did the lower right set of arrows and not the upper left set of arrows. And that's essentially the concept that we're going to talk about. There are two main approaches to model evaluation. One depends on having thresholded your data. And so here, imagine that our whole testing area is this blue square, and our prediction is the red square, and our independent testing data are the yellow dots. Well, all we need to do is calculate the cumulative binomial probability that we would get S successes, which in this case would be 7 successes, out of N evaluation points, in this case would be 8, in a proportion of area, which is with a probability of success of P, which is the proportion of the area that was predicted suitable. So this is a very simple approach, and basically if we're doing much better than random expectations, then we can consider our model as somehow having passed a test of better than random. Sometimes, however, we want to conserve relative suitability information, essentially a ramp between yes and no. And so a very common approach has been the receiver operating characteristic area under the curve, so AUC. And that's very common. It's implemented within Maxent. It's very attractive, very interesting. But I'd point you towards two papers that point out a bunch of problems with using ROC-AUC for niche modeling. So this paper by Lobel and colleagues, and then this paper by myself and colleagues. Essentially, there are a bunch of problems with ROC-AUC approaches, but I'll focus on one, which is that these approaches oftentimes are paying attention to model predictions that are pretty meaningless. So I'm going to go through this very quickly because I'm running out of time. But this is a plot of omission error on a reversed axis and commission error on a non-reversed axis. And traditional ROC analysis essentially looks at, we're looking at the upper left panel in this graph, the elevation of the observed curve, which is that convex curve at the top of the upper left graph. We're looking to see if it is elevated above the diagonal line, which is random expectations. And so in this example, we have an AUC, area under the curve, of 0.8, and the random expectations are 0.5. And so we would probably conclude that we have a pretty good model here. But consider the point on that curve that corresponds to halfway up the vertical axis. That's a model prediction that fails to anticipate half of the occurrences in our independent testing data set. That's not a very meaningful model. So what we do in this partial ROC approach, no time to explain to you all the details, but remember the E parameter, that error parameter. We use that to identify relevant areas of the ROC curve and throw away the irrelevant areas. And so that's what's illustrated in the other three panels. And again, I refer you to that paper if you're interested in this method. I'm going to skip over this for lack of time. Suffice it to say that this procedure has now been implemented in one program in Visual Basic, which is openly available, and now in an R package. It'll be appearing quite soon. Last comment about model evaluation is that significance isn't everything. We can have something that's significantly better than random, but maybe only 51% of the time is right. Well, that's a little bit better than flipping a coin, but it may not be enough for the uses that we need the model to respond to. And so we usually should be pairing significance measures with performance measures. Maybe we need a low omission rate or a high correct classification rate. but we should really always be thinking about significance and performance. Okay, last point, and I'll try to make this brief. I have 5 minutes before the end of the hour, but we scheduled the hangout for an hour and a half, so we should be okay if we go a little bit over. But last point is essentially summing up everything in interpreting. And most of this is going to be specific to a particular use and a particular reason for a study. But I do want to talk about this issue of model transfers and extrapolation. So referred you to another paper from our group, this one Owens et al. And essentially this is speaking about how much we should interpret models that are transferred to other situations. So maybe we're going to calibrate our model across M, that's what we should be doing. And this is essentially a graph of suitability, I'll explain that in a moment, versus values of some environmental parameter. And that's the horizontal axis in this slide. The environments represented across M are shown in light gray, and environments not represented across M are shown in medium gray. And all I want you to see is that our suitability rises at higher values within M. So our occurrence points would be clustered over there against the right margin of the environments within M. That's great. But what if we want to transfer this model, project this model onto future climate coverages or another continent? Very common things done in this field. Well, what's the shape of that curve farther to the right? We don't know. It may taper off in kind of a bell-shaped curve. It may keep going up. We literally don't know because we have no information about that. So this study used a combination, this bigger study, not the one that you see on the page right now. It used a combination of virtual species and real-world examples. And I'm just going to show you one of the real-world examples. This is essentially criticizing a paper that I did, which is fine because I wrote it, criticizing this paper for making some mistakes in over-interpreting the results of the models. So, same sort of diagram. The light area are the conditions within M, and the gray areas are the conditions outside of M. And all I want you to see is that, for example, with respect to temperature, in the left-hand set of panels, our species is reconstructed as seeing suitable conditions at very high temperatures, like 100 degrees Celsius. And that's under two different sets of parameters for Maxent. Same thing goes for GARP, same thing goes for GAMS. My point is, I doubt that malaria vectors are happy when the water is boiling, but default settings in Maxent and removing clamping give us a situation where the species is happy when the water is boiling. And by the same token, when we remove all extrapolation, the species only, this is the bottom left graph, the species only sees suitable conditions under those conditions that are represented within M. And maybe that's not true either. My point is simply that we don't really know what happens under conditions outside of M. So in that paper, we introduce a metric called MOP. And without explaining all the details, the usual percentages of comparison that we want to do are maybe 1, 10, 20%. Where you see red areas are areas that are pretty distant from M in environmental space. And where you see black are things that are strictly extrapolative, and you just should not interpret those models. And essentially the percentages are how much of the two clouds you are comparing. The nearest 1%, the nearest 10%, or all, or half. And all I want you to see is, maybe let's look at the 10% map. There are several areas of Africa where I should not have interpreted that map, and yet I did. My mistake. Those are the black areas. There's some very restricted red areas that you can see, and those also probably should have been interpreted with caution. Anyhow, this is the MOP metric, and it gives us a way of evaluating how much trust we should put in any model transfer. There's already a metric MESS, which attempts to do the same thing. It's interpreted within Maxent, and so it's very convenient. But MESS does the comparison to the centroid of the calibration cloud, not to the nearest edge. And so MESS tends to see the world more pessimistically as far as which areas should be interpreted. And so I would suggest to you that MOP is more of what we're looking for. And what this comes down to is that in environmental space, here's our whole area of interest. This is an environmental space, so the environments associated with G is the dark gray area. But if our M is pretty limited, notice the eta of M, environments associated with M, well, we're going to end up transferring our models onto all of those other environmental circumstances. Now, the species with occurrence data shown as open circles doesn't get close to the edge of the M cloud. And so it should be okay. It should not have big problems with this kind of crazy extrapolation. But the species shown with closed circles, black circles, that species is going to be very hard to model and very difficult to interpret over most of those circumstances in G that are interesting to us, essentially the gray areas that form the left half of this graph. So that's the sort of situation where MOP can help us. And that's also the full spectrum distilled down into an hour. Believe it or not, I did it in almost exactly 60 minutes. But that's a full update on niche modeling methodologies. If a different person working in this field had given this talk, she or he would probably have given you a very different perspective on what are the important points. But I would suggest to you that you read these papers if you're doing niche modeling and digest them and see if they make sense to you. And I hope you'll essentially pay attention to them, because what they're really trying to do is move this methodology towards a more mature approach that is based firmly in ecology and biogeography. Just a last point while I have your ear. Here are some resources in Biodiversity Informatics. With Rob Goralnik and Jorge Soberon, I run a journal called Biodiversity Informatics. It's open access and has no page charges or publication fees. It's simply intended as a forum for discussions about biodiversity informatics. Second element are training resources, which you can access at that linkage that's given in the second bullet point. This seminar series, you can see about future iterations of this seminar series at the Google Plus link, which is the third. And I will be announcing our speaker for the August seminar quite soon. And fourth is a more informal news and communications spot. It's a group on Facebook. It's approaching 2,000 members, and so it's quite active with new data sources and new opportunities. Anyhow, that has nothing to do with the subject of the seminar. That's just pointing out to you some resources. Now, if you have questions for me about things that I've talked about, email them to me as soon as you can. I'm going to check my email very quickly just to make sure that we don't have some questions already. I can see emails from several of you who are seeing them. So, for example, Alan Williams writes to me, and I assume this is about my data cleaning part, where he says, sometimes you need to be aware that borders have changed. So the wrong data may be correct when the occurrence was observed. That's very, very correct, Alan. Which is to say, state borders change, or they get subdivided, or they get lumped, or they get renamed, or the country switches to a new system. And in fact, many times, those internally inconsistent records are more a problem with the base map that one is using for districts or states or counties or what have you. But it's worth checking, and those methods essentially force us to check and make sure that we don't have some problem in the coordinates. But your point is very well taken. Let's see. Now an email from Brian Isabiri. He's just saying hi from Uganda. Any other questions? Again, I'm happy to wait for a little while and see if any questions appear, but not too long. If you have questions, and if we end up cutting off, send me them and I'll do my best to answer. And I'll answer via the Google Plus page so that everybody can see the question and the answer. And again, just to recapitulate, what this talk is all about is taking a field that has gotten a lot of use, which is to say, a lot of people are modeling niches these days. I did some counts a couple months ago, and it was on the order of 300 or 400 papers coming out per year in this field. My hope is that by thinking about issues like this, my hope is that we can move the field towards a better foundation in the concepts. Essentially, do the concepts fit with the goals of our studies? And so we design our methods such that they respond optimally to what we're trying to achieve with these modeling efforts. Okay, well, I'm not seeing any questions. Feel free to send questions as they occur to you. Maybe you're writing right now. Thank you for joining us, and I will have our next seminar announced quite soon. So hope to see you next month as well. Thanks for your time. Bye-bye.